Design this RLC circuit, that is, find a value for R, such that, under DC conditions, the energy stored in the inductor and the energy stored in the capacitor match. Under steady-state DC conditions, we can replace the capacitor with an open circuit and the inductor with a short circuit, like this. The reason behind this comes from the voltage and current formulas. In DC conditions, currents and voltages are constant, so all time derivatives are zero. A current of zero is an open circuit, and a voltage drop of zero is a short circuit, and this explains the simplification we made. With that said and done, the energy stored in an inductor is half Li squared, and the energy stored in a capacitor is half CV squared. Let's label the current through the inductor I, and the voltage across the capacitor V. Remember, the inductance was 4 millihenries, and the capacitance was 160 microfarads. The design problem requires those energies to be equal, so this gives us an equation 0.04 V squared equals I squared. So let's analyze the circuit, find V and I in terms of R, and then solve for R from that equation perhaps. What circuit analysis technique shall we use? Actually, there's no analysis required. Notice that V is also the voltage across the resistor R because it's in parallel with the open circuit capacitor. Also, I is precisely the current that goes through the resistor R. Here's why. The current comes out of the 5 ampere source, reaching this junction. Part of it goes down through the 2 ohm resistor, but the remaining part goes up through the R resistor, and this is exactly the labeled current I. So, by applying Ohm's law, we see that V must be equal to I times R. Substituting this in our equation and applying the square, I squared cancels out, meaning that R squared must be equal to 25, and therefore R must be equal to 5 ohms. And with this, our design is complete.